Hello, you are welcome to my YouTube channel. We'll be looking at Mathematical Methods 1, the lecture series number 2. Last time we reviewed some differentiation concepts. We also looked at implicit differentiation, parametric differentiations, and successive differentiations. Today we'll be looking at Leibnitz Theorem. This theorem is used to obtain the nth derivative of the product of two functions. The theorem states that if u and v are the functions of x, then dnx dx uv is equal to n combination 0 unv plus n combination 1 un minus 1 v1 plus n combination 2 un minus 2 v2 plus plus n combination r un minus r vr plus n combination n uvn. Now proof. In the proof, we are going to use the principle of mathematical induction, which states that first you're going to check for something when n is equal to 1. Is the left hand side equal to the right hand side? Then you move ahead to check if n is equal to n plus 1. What happens? Is the left hand side still equal to the right hand side? And once you're able to show that, then the proof has been done as stated here. Now, let's look at some worked examples. If y is equal to the natural logarithm of 1 plus x all over 1 plus x, we want to show that 1 plus x raised to power 2, y raised to power n plus 2 plus 2n plus 3, 1 plus x, y raised to power n plus 1 plus m plus 1 squared, y raised to power n is equal to 0. We want to show that. So you start by saying proof. Here, applying the equation through, you're going to get this because we are trying to differentiate first. Then when you do that, you're going to have 1 minus natural logarithm of 1 plus x all over 1 plus x all squared. Therefore, if you do a thorough simplification, you're going to have this, that 1 plus x raised to power 2 y prime will be equal to 1 minus y in bracket 1 plus x. Now differentiating again, we have that is differentiating twice now. We are going to have the 1 plus x raised to power 2 y prime prime plus 2 in bracket 1 plus x y prime equal to minus 1 plus x y prime minus y. Now trying to rearrange everything and equate them to 0, you're going to have that 1 plus x raised to power 2 y prime prime plus 3 in bracket 1 plus x y prime plus y is equal to 0. At this point, we are going to apply the Leibniz theorem for the nth time. Now, this is what you're going to get. Applying the Leibniz theorem component wise, that is component by component, you are going to have that dn over dxn of 1 plus x squared y prime prime will be equal to 1 plus x squared y raised to power n plus 2 plus 2n in bracket 1 plus x y raised to power n plus 1 plus n in bracket n minus 1 over 2 prime times 2y raised to power n. Now you do the same thing for 3 in bracket 1 plus x y prime. You are going to get this. You do the same thing for y, then you are going to get this. Adding all terms and simplifying, then you're going to have this long stretch of functions here. So which implies that by the time you collate all the like terms and simplify further, all the y raised to power n plus 2, you group them together. All yn plus raised to power n plus 1, you group them together. Then all the y raised to power n, you group them together. At the end, you're going to see that you're going to arrive at 1 plus x squared y raised to power n plus 2 plus 2n plus 3 1 plus x y raised to power n plus 1 plus n plus 1 squared y n equal to 0 as given in the initial question. Let's look at another worked example. If y is equal to cos arc sine x, we should show that 1 minus x squared y raised to power n plus 1 minus 2n plus 1 xy raised to power n plus 1 minus n squared plus 1 y raised to power n is equal to 0. Proof: let y be given. So the first derivative will give us sin arc sine x times 1 over square root of 1 minus x squared. Now you cross multiply, then you're going to have square root of 1 minus x squared y prime equal to sin arc sine x. Now take the second derivative, then you're going to have 1 minus x squared y prime prime minus xy prime minus y equal to 0. At this point, you can now apply your Leibnitz theorem component by component. So you differentiate the first component here, then the second component, then the third component. Then you now put all the terms together, adding all terms and simplifying. Then you're going to arrive at the answer below, which is 1 minus x squared y raised to power n plus 2 minus 2n plus 1 xy raised to power n plus 1 minus n squared plus 1 y raised to power n equal to 0, which means that we have shown from the beginning that the question given is correct. And let's still take some worked examples. If y is equal to cos the log of 1 plus x, we should prove that 1 plus x all squared, then y raised to power n plus 2 plus 3n plus 1, 1 plus x, y raised to power n plus 1 plus n squared plus 1, y raised to power n is equal to 0. Proof: let y be given. So its first derivative will give us minus sine log of 1 plus x times 1 over 1 plus x. Now, by the time you cross multiply, you're going to have 1 plus x, y prime equal to minus sine log 1 plus x. Now you go ahead to take the second derivative, then you have 1 plus x, y prime prime plus y prime is equal to minus cos log 1 plus x all over 1 plus x. Now, going forward, you now have 1 plus x squared y prime prime plus 1 plus x y prime plus y equal to 0. At this point, you can now apply your Leibniz theorem component by component. Now, the first component is given, and the second component is also given. The third component is also given. Then we put everything together, sum them up, simplify them, and we are going to arrive at the correct answer, which is 1 minus x squared y raised to power n plus 2 minus 2n plus 1 xy raised to power n plus 1 minus n squared plus 1 y raised to power n equal to 0 as required. Now let's look at a subtopic, which is the Taylor's and Maclaurin's theorem. If f of x is continuous in an interval ab, and if a constant variable c is also lies in that interval ab, then f of a plus h will be equal to f of a plus h f prime a plus h squared over 2 factorial f prime prime a plus h raised to power 3 over 3 factorial f prime 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 plus dot 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 plus h raised to power n factorial f raised to power n a. Now let f a plus h be c0 plus c1h plus c2h squared plus c3h cubed. Now, where f prime a plus h will give us c1 plus 2c2h plus 3c3h squared plus 4c4h3 plus dot dot dot. When you continue with f prime prime, and then you put your h equal to 0 in all above, you're going to have what is here. Now, substituting in f in bracket a plus h, you're going to have this. that f of a plus h f prime a plus h squared over 2 prime 2 factorial f prime prime a plus h raised to power 3 over 3 factorial f prime prime plus dot 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 plus h raised to power n over n factorial fn a is called a Taylor's theorem. Why putting a equal to 0 and h greater than x, then the function is called the Maclaurin's theorem. Now f of x is equal to f of 0 plus x f prime 0 a squared over 2 factorial f prime prime 0 plus x raised to power 3 over 3 factorial f prime 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 plus x raised to power 4 factorial, and so on and so forth. Put h equal to x minus a in Taylor's theorem, then you're going to have that f of x will be equal to the summation of f of n a x minus a raised to power n all over n factorial plus x minus a over 2 factorial fn a is used for deriving the Maclaurin series and ascending powers of x minus a. Let's look at more worked example to show that log 1 plus sin x is equal to x minus s squared over 2 plus s cubed over 6 plus dot 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 using Maclaurin's theorem. Solution: let f of x be given, then f naught will be 0, f prime 0 will be 1, f prime x will be minus 1 over 1 plus sin x. When you now substitute x to be 0, you have minus 1. F prime prime 0 will be 1. Thus, f0 will give us x minus s squared over 2 plus s cubed over 6 plus dot 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 dot. So this is the series we are referring to. Now let's look at more worked examples. If y is equal to e exponential sin x, use Maclaurin's to find the series expansion. Solution: let f of x be given, then f of 0 is 1, f prime 0 is 1, f prime prime 0 is 1, f prime 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 0 is 0, and f of 0 at 0 is minus 3. Now the Maclaurin will look like this: f0 plus x f prime 0 plus x squared over 2 factorial f prime prime 0, and so on and so forth. Thus, the exponential raised to power sign of x using Maclaurin's will give us 1 plus x squared over 2 minus s cubed over 8 plus dot 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 dot. Now let's look at more worked examples. We should prove that arctan 1 plus x is equal to pi over 4 plus x over 2 minus s squared over 4 plus s cubed over 12 plus dot dot dot. Proof: f of x is given, and f of x is equal to f of a plus f prime a plus s squared over 2 factorial plus x3 over 3 factorial, and so on and so forth. Now f of a, when a is 1, will give us pi over 4. In this one, f prime also will give us 1 over 2. F prime prime will give us minus 1 over 2. F prime 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 will give us 1 over 2. Now, f of a plus x is equal to f of a plus x f prime of a plus s squared over 2 factorial plus x cubed over 3 factorial f prime 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 a. Now, bringing everything back and putting them together, you are going to see that arctan 1 plus x will be equal to pi over 4 plus x over 2 minus s squared over 4 plus s cubed over 12 plus dot dot dot. By using the Taylor's theorem, we can show that if pi lies between minus pi and 2 and pi and 2, and if x raised to power 4 can be neglected, then this expression can still hold and is very correct. Now let's look at tangent and normal. Recall that if y is equal to f of x, the y dx is gradient of the tangent f of x. The equation of the tangent is given by the y dx is equal to y minus y1 all over x minus x1 equal to m. The equation of the normal is given by y minus y1 all over x minus x1 equal to minus 1 over m. Let's pick some worked examples. If y squared equal to x squared plus 2x, find the equation of the tangent to the curve at the point 3, 5. Solution: let 2y dy dx be 2x plus 2, which implies that the y dx will now be x plus 1 over y. Now do that over 3 and 5. You're going to have 4 over 5, which is the gradient m. Yes, and y minus 5 all over x minus 3, which is equal to the gradient. Make y the subject. You're going to have 4 over 5x plus 13 over 6 as the equation of the tangent. Now the gradient of the normal is given by minus 1 divided by 4 over 5, which is equal to minus 4 over 5, 5 over 4. Hence y minus 5 all over 3x minus 3 is equal to minus 5 over 4. And when you cross multiply and make y the subject, you're going to have minus 5 over 4x plus 35 over 4. Radius of curvature, that is another subtopic. The curvature of a curve is the measurement of the rate of turning of the curve and is given by r equal to 1 plus dy dx squared raised to power 3 over 2 all over the square y over dx squared. The curvature itself is noted by k, where k is equal to 1 over r. Let's look at some worked example. Show that the radius of curvature at any point x1, y1 of x squared minus y squared equal to a squared is x1 squared plus y1 squared raised to power 3 over 2 all over a squared. Solution: let a squared minus y squared equal to a squared at point x1, y1 is x1 squared plus y1 squared raised to power 3 over 2 all over a. Since x squared minus y squared is equal to a squared, then 2x minus 2y dy dx is equal to 0. So dy dx is equal to x over y. And differentiating twice will give us minus a squared over y raised to power 3. Substituting in the formula, you're going to have that your r will be 1 plus s squared over y squared all raised to power 3 over 2 all over minus a squared over y raised to power 3. At this point s1 y1, you have y1 raised to power 3 in bracket 1 plus x1 squared over y1 squared raised to power 3 over 2 all over a raised to power 2. Now your r, simplifying further, will give us x1 squared plus y1 squared raised to power 3 over 2 all over a squared. The negative sign disappears because there is no negative radius. Let's look at another worked example. If x is equal to 3a cos theta minus a cos theta and y is equal to 3a sin theta minus a sin 3 theta, show that r, the radius of curvature, is equal to 3a sin theta. Let dx d theta be a minus 3a sin theta plus 3a sin theta. Then dy d theta will give us 3a cos theta minus 3a cos 3 theta. Y dy dx will now be dy d theta times the x d t divided by dx d theta. And if you do that, you're going to have sine 2 theta over cos 2 theta, which is tan 2 theta. Therefore, the dy dx is tan 2 theta. Differentiating twice will give us 2 sec squared theta, but dx d theta is equal to minus 3a sin theta plus 3a sin 3 theta. Hence, the square y over the x squared is equal to 2 sec square theta all over minus 3a sin theta plus 3a sin 3 theta. But sin 3 theta minus sin theta is equal to 2 cos 2 theta sin theta. Thus, the double derivative, the square y over the x squared, will be equal to sec cube 2 theta all over 3a sin theta. Substituting into the formula, we now have that r is equal to, which is r equal to 1 plus dy dx squared 3 over all raised to power 3 over 2 all over the square y over the x squared will now give us, when you substitute properly, you are going to see that you have 3a sin theta. So we've been able to show that the radius of curvature r is 3a sin theta. Thank you very much for listening. Bye.